Here's the rules. So we're going to unfreeze this so that we can see what's on the screen. There we go. All right, so we're going to have a player choose one Starburst from a bag. So here is our special Starburst Grab Bag for today's game. And we're going to record the results, and we're going to record what color that first Starburst is. Then the player is going to choose a second Starburst from the bag, and this is going to be done without replacement. So they're not putting the first one back in, they're just going to hold on to the first one, and then go ahead and grab the second one, and we're going to record the result color of the second Starburst. And the player is going to win if the two Starbursts are matching in color. We're going to try this out. So we're going to play this game 10 times as a class, and we'll all go ahead and record the same class results here on the table. All right, so based on the results here of our 10 games, what is the probability of winning this game? Go ahead, Tanner. Close. Okay. Yep, there you go, 20%. So we won 2 times out of 10 total games. So 2 out of 10 would be our experimental probability. So let's go ahead and add that word in when it says the probability of winning the game. Well, this was actually just based on what happened. And it's certainly possible that if we were to play this another 10 times, we might have a different result. And so that's just an experimental probability. All right, well, we are going to move forward looking at investigating what is the theoretical probability of winning this game. And in question 2 here, it says, well, what other information would we need to know to calculate the theoretical probability? Is there anything that you were maybe wondering about regarding the contents of the bag? Is there any information that we're missing? Go ahead, Bernie. Yeah, exactly. I never told you how many there were, and I didn't tell you how many we had of each color. So that's going to be really important if we want to try to figure out the theoretical probability, what we would expect to happen in terms of winning this game. All right, so I'm going to reveal the contents of the bag. So we have seven Starbursts. 5 of them were red, and 2 of them were yellow. So let's go ahead and record that here, that we actually had 5 red and 2 yellow in the bag. All right, so what we're going to continue with today is another kind of visual model, kind of like the two-way table, but this is going to do something a little different for us, today, called a tree diagram. And this model is going to help us to calculate the theoretical probability of winning the game. So we're going to start here at the very beginning. You'll notice that we have 2 possibilities here in the Starburst game for the first Starburst. So we have this option here, this branch, is that the first Starburst pulled out is a red. This option down here, the first one pulled out is a yellow. Well, if we have 7 Starbursts altogether, in the form of a fraction, what would be the probability that the first one is a red? Go ahead, Mark. 5/7. So that would be, that's the theoretical probability here, because it is the number of ways that we can get red, and that would be 5, since we have 5 of them. The denominator is the total number of possible outcomes, in this case, the total number of Starbursts that we could have grabbed. So then what is the theoretical probability that the first one was a yellow? 2 out of 7. We had 2 yellows in the bag out of 7 total. All right, so now we're going to look into the second set of branches here. Now, one important detail in this game is that it was done without replacement. So once the first Starburst was taken out, we did not put it back in the bag. So with the colors up here, so I want to try to model this first branch of the first one being red. Well, if the first one is red, I'm now taking one away. How many Starbursts are left in the bag? Now there's only 6. So our probability is going to slightly change when we fill in the next set of branches. So out of these 6 that are left, what is the probability now that the second one is red? How many reds are left? Just 4 out of the 6 total. So it's going to turn into 4 out of 6 that the second probability, or the second Starburst was a red. What then would be the probability that the second one is a yellow out of these 6? Now it's just 2 out of 6. All right, so at the end of the 2 sets of branches here, we see that we have a little box. And what this is going to do, this is going to be a place for us to write the calculation of the first one being a red and the second one also being a red. So you'll notice that probability notation off to the side there, that if we were to completely follow through these 2 branches, if both of these 2 events happen, our probability is going to be found by multiplying the 2 fractions that are along the path of the branches. So the probability that the first one was a red was 5/7, and we're going to multiply that by the probability that the second one is red, which was 4/6. Now when we're multiplying with the fractions here, we're just going to multiply across the top, and we multiply across the bottom. And for today, let's go ahead and just leave that in its initial form there of 20 out of 42. But we could turn that into a decimal, we could turn that into a percent if we wanted to, but that's going to be the probability that our first choice was red and the second one was red. And let's also just make a little note here that that was one option for winning the game. Because we know that we just need to get our colors to match, and that was one way that that could happen. All right, so I would like you to now look at filling in the rest of this tree diagram. So see if you can fill in all of the empty boxes, and then we'll come back together here to check in just a couple minutes. All right, so this is what the rest of our tree diagram should have looked like. So for the first little piece here, we figured out the 4/6 and the 2/6 split. To get this answer over here, the 10 out of 42, we're kind of just thinking about the same thing. If the first one is red and the second one is yellow, these are the 2 pieces that will multiply. But then what's interesting is that our fractions change a little bit when we're looking at the second pathway, and that's because when we take the first one out, if the first one happens to be yellow, I want to model that here, so the first one goes away, we still have just 6 left in the bag, but notice how we still have all 5 reds. And so that's why we have 5 out of 6 is the chance that the second one is a red. But now that one yellow is gone, it's only 1 out of 6 the chance that the second one is a yellow. And then again, just multiplying through those branches to get the remaining probabilities there at the end. So a couple of things here. So this probability answer we got after we multiplied the pieces together, that's always going to be the result of the first event happening and the second event happening. And so this is a little different from the language that we have been using over the last couple of days. We have seen probability questions with the word or. Remember the Skittles problem. We wanted to know the probability of a green Skittle or a purple Skittle. We added those probabilities together. Well, in this example here, because we're finding an and situation, the first event happening and the second one, the individual probabilities are being multiplied. Another thing that I want you to notice here, for these final answers here at the end, all of the little fractions out of 42, they should all add up to 1. And so if we were to think about adding those numerators, 20 plus 10 plus 10 plus 2, The numerators add up to 42. Now, when we are adding fractions, we just want to add the numerators and keep our denominator the same. So we see that they all add up to 42 out of 42. And this is a helpful thing to think about and know that whenever you're making your tree diagrams, these values here at the end should always perfectly add up to 1. So that can be a way just to double check to make sure that you have the branches labeled correct and you've done the multiplication part correct. Okay, so we see here that we have two possibilities for being a winner in the game. So we saw the first one is that they're both red, or the situation very at the bottom is that they're both yellows. And so we are going to use those two things to help us answer question 4, which is that actual theoretical probability of winning this game. So we're going to take the 20 out of 42 answer, and we're going to actually add that to the 2 out of 42, and that will give us a theoretical probability of 22 over 42. And when we're doing that, it kind of does turn into an OR problem for just a moment, because we're finding, all right, what is the probability of winning with red or winning with yellow? And they're mutually exclusive, so they cannot both occur at the same time, and so we just want to simply add the individual probabilities together. So here's what that would look like here for part 4. And in the space over here at the side, so if we were to kind of put words to this, connecting to what we've done previously, it was the probability of winning with red or winning with yellow. And that's why it turns into the addition rule right here, because we're using the word or. Now, if we just take a quick moment to, if we were to divide that out and turn it into a decimal, 22 divided by 42, we do end up getting that the theoretical probability of winning the game is 0.52. So that was actually quite a bit higher than our class result. So as a class, our experimental probability of winning the game was only 0.20. So we were a little lower than theoretically what would happen, but that's okay. That's what sometimes happens with experiments. Now, the more times we played the game, if we had played the game 100 times or even 1,000 times, we would get closer and closer to that theoretical value of 0.52. All right, let's look at question 5 here. So now it's asking, what is the probability that the first starburst was red, given that the person won the game? So this is now a conditional probability with that word given, which was something that we looked at yesterday. Let's first see if we can turn this into the proper notation. So we want to find the probability that the first one chosen was a red, given that the person won the game. Well, we're going to report this probability out as a fraction. And remember that when we talked about the conditional probabilities before, it was always the probability of the second part, what the condition is. So given that the person is a winner, is what's going to go down here on the denominator. And so we could write that in decimal form as 0.52. I'm actually just going to keep mine in fraction form, 22 over 42. So that would be like the probability that the person won the game. And then what we're going to fill in for the numerator part here is the probability that their first starburst was a red and they won the game, which really means they both had to be red in order for that to happen. So if we go ahead and look back at here, the only option that provides a winner where the first starburst was red is this one right here. And so we're going to go ahead and take this little probability right there, of 20 out of 42, and we're going to transfer that over here to become our numerator. All right, and if we were to put just a few little labels off to the side here, so on the denominator, it's really just the probability that the person was a winner. The numerator here was the probability. Let's rephrase this a little bit. We're going to say the probability that the first one was a red and the person was a winner. All right, now there's a couple of things that we can do here to get our final answer. We could turn them both into decimal form and then just divide them on our calculator. So, for example, on the bottom here, we already know that that's 0.52. We could figure out what this is as a decimal and then just divide our decimals. Another thing, though, that's cool that I wanted to show you here with keeping these in fraction form is that if you have a fraction divided by another fraction, and they happen to have the same denominator, you could think about just canceling those two denominators, and it's really just going to be the division of the numerators. It's really just the same thing as 20 over 22, which we could then put that into a calculator, and we end up getting that that result there would be 0.91. And you can test this out both ways. If you turn 20 out of 42 into a decimal, divide that by the 0.52, we should still get the same answer of 0.91. So what this is telling us here is that, well, that's a pretty high probability that if the person won the game, it's highly likely that they won the game with red, 91% chance that it was red, versus only like a 9% chance that they won the game with yellows. Did we have any winners with yellows? I don't think we did. Yeah, the only wins that we had were both with reds, which kind of makes sense because there was a lot more reds in the bag, so it makes sense that it would be a lot more likely that that would be the case. All right, now before we turn over to the back, I want you to grab your different color if you haven't already done that. We're going to actually go back and just add a couple of additional things, and then we'll summarize on the back side. So going back up here to the top, so one thing that I want you to fill in, so I'm going to switch to my different color, I'm going to switch to red, is this whole idea of taking out a Starburst from the bag without replacement. So the fact that we did not have replacement means that our two events of first Starburst grab versus the second Starburst grab, we call those dependent events. And that just means that the results of that second grab were dependent upon whatever happened with the first grab. And we saw it happen in the tree diagram, that once we took that first Starburst out, our probabilities actually changed for what would happen for the second one. Now here's the difference. If we had played the game under different rules, and we had played the game with replacement, so first Starburst taken out, put it back in the bag, second Starburst taken out, put it back in, that would be considered independent because the result of that second grab will not be affected or changed based on what happened with the first grab. So that's one of our learning targets for today, is to decide if two events are independent. So independent would mean that the events don't have any influence on one another. That was not the case here, though, for our game, so we call them dependent. All right, a couple things that we're going to add in here to our tree diagram. So this calculation that we're figuring out here, the probability that the first Starburst is a red and the second one is red, this is actually a conditional probability. And if we were to write that out with our notation, hold on a second. We're going to go back to that little part here. This is the one that I want us to label first. So go ahead and point to that fraction, that 4/6. So this one right here is a conditional probability. So the way that we got that 4 out of 6 is that, well, there had to be a certain condition being met at the start. Before we did that, the condition was that the first starburst was red. This was then the probability that the second one was red. All right, so here's how I want us to label the fractions over here in the box. So first off, that 5/7 is just the probability that our first starburst is red. And that was being multiplied by the second fraction there. So the 4/6, the one that's a conditional probability, this is now the probability that the second one was red, given, so we're going to put that vertical line in, given that the first one was red. All right, and then one other little note that we're going to add here in this space off to the side about these being dependent events that we're representing. A way to put that into words is just that the probability of the second starburst depends on the outcome of the first. All right, so now when you're ready, we'll go ahead and turn over to the back side. All right, so we have 3 learning targets for today. We're actually going to give ourselves like a big wide space for the first learning target, and then we'll divide the bottom there for the second and third. So the first one here that we just mentioned was to decide if 2 events are independent. So we're going to start with that one, like a definition here. So independent events, this is where the outcome of one event does not change probabilities for another event. So independent would be like sampling with replacement. So chances of getting a red on the first pick, 5 out of 7, put it back in. Chances of getting a red on the second pick would still be 5 out of 7 because they're all still there. So that would be if our 2 events are independent. All right, and then what we actually had in the game were dependent events. And what we're going to say here is whether or not one event occurs does change probabilities for another event. And that's when we are sampling without replacement. All right, our second learning target here was to apply the general multiplication rule for any two events. So this is where we want to find the probability of a first event and the second event. So here we have the probability of A and B. And this is what we saw as the end result of following the branches in our tree diagram. Where the multiplication happened is that we had the probability of the first event, so probability of A happening, and that was being multiplied by the probability of the second event, given that the first event happened. So we'll write that as probability of B, given that A has already occurred. So with the Starburst thing, this was like the probability of getting a red on the first pick, multiplied by the probability of getting another red, given that the first one was a red. That's how we figure out that second piece. All right, and then learning target number 3 was all about using tree diagrams to find the probability of more than one event occurring. So the general idea with the tree diagrams is that we have a starting point somewhere over here on the left, and we're going to begin to branch this off. And if we think about there being two possibilities here, if we call the first possibility A, the probability of the other situation down here would be 1 minus the probability of A happening. Remember that not A is called A complement, and we do the little C up here to say, well, that would be the opposite of event A happening. For us, we had only two colors in the bag, so this was red, and then not red, well, it was actually yellow. Usually we would just label it with whatever color it is. We don't necessarily need to write the word not red. We can just say yellow, but symbolically that's what that would be represented as. And then we could have multiple layers here. So in ours today, we had a second set of branches because we had a second event, B, and this would kind of look the same way. So like the first possibility is B happening. So the other possibility would be not B, or B complement. And we'll have the same two choices down here. All right, and then following the path of the branches and multiplying those probabilities that we label along the way, this first pathway here, that end result is going to be the probability of A and B. Following this path of the branches there would give us the probability of A and B complement. Moving down below here, the next pathway that looks like this, multiplying those will give us the probability of A complement and B. And then the last pathway all the way down here at the bottom will be the probability of A complement and B complement. And the main thing about those, like 4 end results there, is that they must add up to 1. So in ours, that's where we had all of those separate fractions that were all out of 42. We saw that they all added up to be 42 out of 42. All right, so we're going to have a chance to try this out now with the Check for Understanding problem. So we're going to read through a scenario that's going to give you information needed for you to construct a tree diagram to model the chance process. And then you're going to answer a series of questions based on your tree diagram that you create. So it says that Chakoi has a Spotify playlist with over 1,000 songs. All the songs are classified as either pop or rock. with 40% of them being pop and 60% of them being rock. Now, of the pop songs, 80% of those are short, meaning less than 3 minutes, while only 25% of the rock songs are short. Suppose that Jacoy uses shuffle play to choose his first song of the day. So again, you're going to start with the tree diagram here in part 1, and then use that to answer the questions down below. I'm going to give you a little bit of time to work on that. I'll be around the room to kind of check in with you as you're working. Feel free to also talk and check in with the people that you're sitting with, and then we'll come back together here as a class in just a little bit. All right, everyone. So we're on about 10 minutes. I thought now would just be a good time for us to come back and check in. So I'm definitely seeing a lot of good ideas here for getting our tree diagram set up. We're going to talk here just to make sure that we are all on the right track. We have the correct numbers and labels in the right places. And then from that tree diagram, we'll see how we can use that to answer our questions. So the starting point over here on the left, you can write the word start like we did up above, but we can also write a word that just describes what's happening in our context. So because we're dealing with all of the possible songs that could be chosen, I'm going to write all songs. And initially we have like this first set of branches that's going to give us 2 possibilities for the type of song. So it says that all of the songs are classified as either pop or rock. And it's telling us here that 40% are pop, so I'm going to write point 40 along this branch, and 60% of them are rock. All right, so that's our first split. Notice every little split that we have, these 2 probabilities add up to 100%. Those add up to 100. All right, so now if it's pop, so looking at the first possibility, we now have 2 more options, and that is going to be the length of the song. So it's telling us 80% of pop songs are short. I'm going to say that that is our next possibility here, and it's 80% of those, so we have 0.80. What would be a word that we can use? What's like the opposite of short? You can say long. And so if 80% of the pop songs are short, what percent of them would be long? 20%. So we'll go and label that as 0.20. Notice that this next little set of branches, these add up to 100%. Let's go down and do the same thing below with the rock songs. We're going to split this into short and long. And so going back up to the problem here, it's telling us that 25% of the rock songs are long. So that was given to us in the problem. So what percent of the rock songs would be short?
Actually, seeing that 25% short.
So 25% is long. All right, so we're going to subtract that from 100%. So that would just mean that the other 75% would have to be short. So all together, this adds up to 100% of the rock songs. Yes, you're right. Oh, yes, thank you. You're right. You are right. I don't know what I was thinking there. All right, yes, so let me switch these around. So we still have the 25% and the 75%. Not paying attention there. All right, so it's going to look here like this. Great. Okay, so some of these labels, notice how they were given to us directly in the problem, but some of them we had to solve for. But we're just going to use a little bit of logic, use some thinking to figure out, okay, what that other percent would have to be. Okay, so we're not finished yet. This is where we're going to actually use our tree diagram. We're going to travel through the branches. And this is going to help us to represent 4 possible outcomes for the type of song that can be chosen. So following along this first set of branches here, this is really going to be the probability that it's a pop song and it's short. And the way we'll get that is by multiplying the 0.40 by 0.80. And we can just leave that as a decimal answer, so all together, that probability would be 0.32. I'm just going to continue to fill in the rest of these possibilities here.
Yeah.
All right, so now that we have those 4 situations here filled in, if these 4 values here at the end that are highlighted, these are the ones that need to add up to 1. And if we check it here, so that 32% plus 8%, so that's like 40% or 0.40. Down here at the bottom, 0.15 plus 0.45 is 0.60. So sure enough, those 2 pieces are going to add up to equal 1. All right, so we're going to use our tree diagram here to start to answer the question. So first off, in number 2, it says describe the meaning of the 80% of 0.80 in the tree diagram. So I'm just going to highlight this little piece right here. And that meaning is just that given the song is a pop song, there is an 80% chance that it's short, meaning it's under 3 minutes. So given that a song is pop, there is an 80% probability it is short. A way that we can write that sentence or that phrase out symbolically would be the probability that the song is short given that it was a pop song. All right, in part 3 here, what is the probability that a short pop song is chosen? Well, this is an answer that we already calculated up in our tree diagram. So the probability that it's a pop song and it's short, that was the pathway that we followed across the very top of our diagram. So we've already done it. It was the 0.40 multiplied by 0.80 answer. That probability was 0.32. All right, the next one, what is the probability that a short rock song was chosen? Whoops. I'm getting all mixed up today. So the probability that it's rock and short, so that was like the 3rd pathway that we followed in our tree. So that was the result of doing 0.60 multiplied by 0.25, and that gave us 0.15. All right, so we're going to use those 2 pieces that we just found in number 3 and number 4 to help us overall find the probability that a short song is chosen. Well, we have 2 possibilities here. It could be a short pop song, or it could be a short rock song. So it's going to turn into an or question, which just means we're going to add the previous 2 probability answers we got. So it could be short pop, or it could be short rock. And that word or is why we're now adding the pieces. So it's actually a 47% chance or a 0.47 probability that the song ends up being short. All right, in part 6 here, given that the song selected is short, what is the probability that it was a pop song? So we're going to finish with a conditional probability here. Whoops. So in other words, what is the probability that it's a pop song given that it was a short song? All right, so for the conditional probability here, we're going to set it up as a division problem. We're going to set it up as a fraction, where the denominator part is always the probability of whatever the condition was. Now, we just figured out in the previous step the probability that it's short was 24/7. So that's our denominator. So in other words, out of all the possibilities that end up being short. And then the numerator here is the probability that it is a short pop song, which we also know that right up here. That answer was 0.32. All right, so then we'll go to our calculator here. For the final step, we'll go ahead and type in 0.32 divided by 0.47. And we get a final answer here of 0.68. So in other words, 68% of the short songs were in the pop category. And then really quick here on page 10, so I was just looking ahead to some other questions similar to what we did today. The wording is a little different here, so we're not making a tree diagram at the very start. It's given us some information about a chance situation, and it wants us to write out the sample space of all the probabilities. So the sample space, that would be like just a list, if we were just to list out what all the different situations are. So it says that Reese doesn't trust the shuffle feature for treating music, so she's developed her own system. She made a list that ranks her top 6 favorite artists. So it says that every day she's going to roll a die, like a 6-sided die, to determine the artist, and then she's going to toss a coin to determine what streaming service she's going to use. So if it's heads, she'll use Spotify. If it's tails, then she'll use Apple Music. So as we start to write out the sample space, here's kind of an example of how it would look. So 2 possibilities could be if she were to roll a 1 on the die. If she got a 1 and heads, it would be BTS on Spotify. If she rolled a 1, but then she flipped tails, then it would be BTS on Apple Music. And we would just continue that all the way through. So really, every single artist is going to have 2 possibilities. So we would have like Taylor Swift on Spotify, or Taylor Swift on Apple. And then we would have Drake on Spotify, or Drake on Apple. So it's actually going to end up being 12 possibilities, 12 outcomes here when you're listing out your whole sample space. So then we know that it's out of 12. So that'll be super helpful to do at the start to help you answer those 6 questions there on number 10.